From our last lesson, you noticed that the law of sines led us to something called the circumcenter of a triangle. You may have asked yourself, is there an analog that the law of cosines leads us to? The answer is yes, and it's called the incenter. Although it might take us a while to see the connection to get there, so I'll break this into a couple different parts. With the circumcenter, construction was made by bisecting the side lengths. In an interesting way, the incenter is constructed by bisecting the angles, meaning cutting the angle in half, so that this angle is equal to this angle, this one to this one, and this angle is equal to that angle. It can be done with a compass and a straight edge. So given an arbitrary angle, I set my compass to a convenient length. Doesn't really matter what, as long as I keep it the same throughout. And mark off two spots, one here, one here. Then from these 2 points, I will draw another arc, one here and one here. Notice there's an intersection. Where they intersect, I will connect a straight edge and draw a line. From the vertex of the angle to the intersection. And that is a bisection, meaning now I've cut the angle in half. This angle here is equal to this angle here. More practically, angle bisection can be performed with a simple protractor. Notice my modification to our previous drawing with color coordination to help you visualize. Take a look at this and give yourself a moment to digest it all. We've already established that the two orange angles are equal to each other, likewise the blue and the green. The yellow line represents the radius of the incircle. Because it is tangent to the triangle side at each intersection, that makes this a right angle, here and here and here. So now we have a case of similar triangles. This triangle being similar to this one, this triangle being similar to this one, and this triangle being similar to this one. You can visualize it by flip-flopping back and forth and seeing the mirror symmetry. This will be very important to help us derive our result. I start with the familiar method of labeling the angles in my triangle A, B, and C, with the opposite sides matching, A, B, and C. Now I define an important quantity S, which is A plus B plus C divided by 2. In other words, it's half the total perimeter of this triangle. This may look a little confusing at first, but if you stare at it long enough, it'll probably make sense. Notice, for example, how I've broken side length B into S minus C plus S minus A. Similarly with C being S minus B plus S minus A, and side length A being S minus B plus S minus C. Notice the side lengths match. Green and green, blue and blue, orange and orange. Green and green being S minus C, blue and blue being S minus B, orange and orange being S minus A. My chalkboard became too small for this concept, so we're going to try something a little different. Take a look at the diagram as we go through this discussion. We had defined S is equal to A plus B plus C divided by 2, which is just half the perimeter of the triangle. The top line states that S minus B plus S minus C is equal to 2S minus B minus C. Doing a bit of algebra and canceling, we find that this quantity is equal to A. That matches what is drawn on the diagram. The same reasoning can be applied for sides B and C. If you're confused why we have chosen to use this quantity S, don't worry too much. Bear with me as we follow through with the algebra, and you'll see why. Take a look at the orange sides, representing length S minus A. Remember that the yellow segment is the radius of the incircle, which is perpendicular to the triangle sides. This means there are two similar right triangles here, oriented symmetrically along the hypotenuse. The angle A is bisected into equal angles. Tangent being opposite over adjacent, we can say that tangent of A over 2 is equal to R over S minus A. Cotangent is simply the reciprocal of tangent by definition, so cotangent of A over 2 is equal to S minus A divided by R. Rearranging, we can write R times cotangent A over 2 is equal to S minus A. A similar argument applies to the other two angles, as shown below. Now we substitute the previous result into our first equations. I have shown the first case for side length A, using color coordination to help guide your eyes. In a similar way, the substitutions for sides B and C can be made. If I add the three equations together, I get this result. 2r times cotangent A over 2 plus cotangent B over 2 plus cotangent C over 2 is equal to A plus B plus C. If I divide both sides by 2, then the right-hand side is now equal to S. Finally, I divide both sides by r. This gives me cotangent A over 2 plus cotangent B over 2 plus cotangent C over 2 is equal to S over r. Save that thought. We'll revisit this in a moment. Remember from our trig identities that tangent of alpha plus beta is equal to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Taking the reciprocal of tangent and following through with the same derivation, it can be shown that cotangent alpha plus beta is equal to cotangent alpha times cotangent beta minus 1 over cotangent alpha plus cotangent beta. Feel free to revisit that lesson if you need to brush up. Things get a little more complicated when we add 3 angles instead of 2. I've simply split the argument u plus v plus w into 2 parts, u and v plus w. Then I've nested one angle sum identity into the other, as shown in the square brackets. In the next step, I've added cotangent v plus cotangent w divided by cotangent v plus cotangent w in rounded parentheses. Remember that anything divided by itself is equal to 1, and anything multiplied by 1 is equal to itself. So why did I do this? I wanted to have a common denominator on all 4 terms. That way I could add the fractions and cancel it out to simplify. The final result is the product of cotangent u, cotangent v, and cotangent w minus their sum divided by that denominator. Notice that the pattern cotangent u times cotangent v, cotangent u times cotangent w, and cotangent v times cotangent w. Multiplying each of these terms by -1 simply changes the sign from positive to negative and vice versa, which leaves me with the result in the final line. Now suppose the sum of u, v, and w is equal to pi over 2, or 90 degrees. That means the cotangent of u plus v plus w is equal to cotangent pi over 2. From the unit circle, we know this is equal to 0. Setting cotangent u plus v plus w equal to 0 is the same as setting the numerator in our previous identity equal to 0, because 0 divided by anything is 0. Warning! 0 in the denominator is a very different thing. Do not do that. Back to the main point. The numerator set equal to 0 gives us the sum of cotangent u, cotangent v, and cotangent w equal to their product. Remember that the sum of angles in a triangle is equal to pi radians, or 180 degrees. That means a over 2 plus b over 2 plus c over 2 is equal to pi over 2 radians, which satisfies the above relation. So in conclusion, cotangent a over 2 plus cotangent b over 2 plus cotangent c over 2 is equal to cotangent a over 2 times cotangent b over 2 times cotangent c over 2. That being said, we now return to this expression, as promised. Substitute the sum of cotangents for their product. Next, we substitute these guys from the beginning of our discussion, which gives us this. r times r times r is equal to r cubed. Cross-multiply to get s minus a times s minus b times s minus c divided by s is equal to r squared. Take the square root of both sides, and we have an expression for the radius of the incircle in terms of the triangle's 3 side lengths. Here is an overview of the entire process in all its glory. Pause the video and take as long as you need to digest it all. Of course, you can go back and replay individual portions in which I explain how we get from one step to another. Thank you for watching this video. In another lesson, we will show how the incircle is related to the area of a triangle and the law of cosines. Stick around for that. In fact, subscribe to my channel so you can be notified when I post new lessons. Like and comment as well. I look forward to seeing you next time.